Good day everyone. Today's video lesson is about ray diagram and mirror equation. In particular, we have the concave mirror. Now supposedly these two topics should be separated, but I have decided to combine this as one so that you'll be able to appreciate ray diagram together with mirror equation. So let's start. So first, let's try to find out what is ray diagram. So by definition, a ray diagram is a technique that you will use to be able to locate and determine the image formed by a mirror. So it uses geometry, it uses lines for us to understand where the image is formed. Now, in writing or in doing the ray diagram, there are rules that we have to follow in locating the image. So we are going to uncover these rules one after another. Now, talking about mirrors, so there are two types of curved mirrors. One is the concave mirror. Second is a convex mirror. Now, earlier in our discussion, in the previous meeting, we talked about plane mirror. So your plane mirror is different from this type of curved mirrors. Specifically, concave spherical mirror is also known as a converging mirror. So this type of mirrors are used whenever a magnified image of an object is needed. So let us try to understand through a ray diagram how a concave mirror magnify or can produce a magnified image. Now, so this is how we are going to determine the image using a ray diagram. So this represents the concave mirror. As you can see, it is forming an inverted C. So if you happen to be confused about concave and convex, just remember the word cave. So cave, as if you're entering a cave, an opening in the cave. So that's concave. And this line here, the central line, is called the principal axis. And then followed by from this principal axis, the closest point other than the V or the vertex is F, which represents the focal length. So your focal length is half of the radius of your spherical mirror. So if you're going to extend this mirror, the spherical mirror as a whole, half of the radius of the spherical mirror is your focal length. Okay, and twice the length of your focal length or focus is called the center of curvature, which is represented by C. So let us try again to identify these parts of your concave mirror. So this surface here, inverted C, is your concave mirror. F here represents the focal length or the focus, while C here is the center of curvature. Okay, let's continue. Now this time we put an object in front of a concave mirror. So it is expected that an image will be formed from it. Okay, so how is an image formed through ray diagram? So first we notice that there is an incoming ray of light that hits the mirror. So that ray of light is coming from the top portion of the object, and it is moving parallel to the principal axis. So that's the first rule. Ray of light passing parallel to the principal axis, when it hits a concave mirror, it will be reflected. So we expect a reflection from this once it hits the mirror, and the reflected light is, there you go, it passes through the focus. So your red light represents the incident ray of light, while your blue light represents the reflected ray. Okay, so a ray passing or a ray parallel to the principal axis is reflected passing through the focus. Okay, so that's the first rule. Next, another ray of light coming from the top, again coming from the topmost part of the object, another ray of light passing through the focus. Okay, so once it hits the mirror, it will be reflected. Okay, once it hits the mirror, it will be reflected parallel to the principal axis. Okay, so here, a ray of light passing through the focus will be reflected passing or parallel to the principal axis. Okay, so you just have to remember two words. One, parallel towards focus. Second, focus towards parallel. Okay, so those two rules of ray diagramming is enough for you to come up with an image. So the intersection of this reflected ray is where the image is formed and where the image is located. So you notice these two intersection or this intersecting reflected ray. So that is where the image is formed. So since this ray of light is coming from the head of the object, so common sense will tell us that this is also, the intersection is also where the head of the image is. Okay, so there you go. You have your image as represented by the green arrow, while the object is that of the purple arrow. Okay, so that's how we come up with image using ray diagram. The problem here is we are not certain, we are not able to determine the distance, the accurate distance of the image from the mirror. At the same time, we do not know the accurate height of the image. What we only see is the location of the image in relation to the object. But we are not able to identify how far it is from the mirror and how tall the image is. This is where mirror equation comes in. So that's why I said I will integrate ray diagram and mirror equation. So for us to identify how far the image from the mirror, we will be using this mirror equation. So the formula suggests 1 over DO. So your DO here represents distance of the object. So this distance from the mirror towards the object is called your DO. Plus 1 over DI. So DI here represents distance of the image. Okay, so distance of the image, the length of the image from the mirror. That distance of the image from the mirror is distance of the image. Is equal to 1 over F. 1 over F, or F here means the focal length. Okay, so that focal length is equal to your F. Okay, another valuable component of the mirror equation is this, represented by M. M here refers to the magnification, or it tells you how many times the image is magnified. So that can be achieved if you are going to divide hi, meaning the height of the image over the height of the object. So comparing the height of the image and the height of the object, so dividing the two will be able to determine the magnification. It will tell you how many times the image is magnified. Now, if ever you're not, you can also use the DI and DO component to get the magnification. So from the formula, it says negative DI, which is this, divided by DO, or the distance of the object, which is this length here. So dividing these two can also give you your magnification. Okay, so that's how we are going to use mirror equation to determine how far the image is from the mirror and how tall the image is. So moving on, as I mentioned, so that's your mirror equation together with this. Okay, so specifically we have a problem here. Now, an object is placed 12 centimeters in front of a concave mirror with a focal length of 8 centimeters. So, from a mirror, you have your focal length, half the radius of the sphere. So, just beyond, or a little beyond just over your focal length is where the object is placed. Okay, 12 centimeters away from the mirror. So from this, you're going to calculate the position of the image, or you meaning to say the distance of the image from the mirror. Second, the magnification of the image. How many times the image is magnified, or is it magnified or reduced in size? And the third, from your results in numbers 1 and 2, from those numbers, you're going to interpret these numbers into the nature of the image, whether it's real image or virtual image. You will also be able to identify whether the image is inverted or upright. And you'll also be going to identify the size of the image. Is it magnified, reduced, or same size of that of the object?